Next step beyond that is so now this current in the primary is sinusoidal with a zero average. Why? Because this capacitor is charge and discharge. You understand? Just like in a Ćuk converter. On the primary side, this capacitor being charged and discharged dictates that this current has to have DC average. This capacitor is doing the same thing in a Ćuk converter. Now, if you have on the output, now the current DC, all right, now the output will have this current, this transformer is square wave voltage driven from primary to secondary, but this current on the primary, just like any transformer, generates its corresponding secondary current. So if this current is sine wave, what has to be happening to this current? Has to be sine wave current. So this magnitude is a turns ratio of this to this 1 to n. It is stepping up. So this current here will be n times I primary. So I secondary is n times I primary. I primary is AC. So this has to be AC. But is this the only one? No, because it has a DC level of the load. So this secondary current is this plus DC load current. And that's why this is what we needed for driving microprocessors. You understand? Because now the DC load current will create this to be 2 times I. So peak to peak sine wave current will be DC level and this AC current multiplied for primary. So you see, that's what we needed for a really single converter, single module, which will have a direct built-in large transient without, pulling. When this changes suddenly from one current level to another, I1 to I2, then this current level will dictate the magnitude of resonant current pulled from that converter. So this converter is DC voltage source to DC output, essentially. Why? Because, yes, this will have this, but what about if I put another converter identical with this and just shift it by half a switching period? Then I will have the other one current like this. And unlike in a transformer of a Tesla with a two-phase currents, 180 degrees don't cancel, here is you need a three-phase. But here with the two-phase system, two identical converters shifted for 100, so you have just a pin which will shift it for half a period, switching period. These two currents cancel, and what do you get? Black, which is ultimate ripple current of these two converters. So what do you get then? You get a two-phase converter, two identical converter. You don't need a 12-buck converters. You don't need any buck storage energy. You don't store energy, and what is the capacitor on the output? Not much, because this is a 2% of DC current, or 5% DC ripple current at twice the frequency. So therefore, this can be small, and because it is driven by the DC source current, that's why this will now do both things. In a single cycle or sub-cycle, you'll have the transient die down, and also you will have the ripple small, so this capacitance is small. And what's good? That large step down, n to 1 in the voltage, will large step down in voltage, in opposite will be large step down in current. So if this is 100 volts, 100 amp current on a DC current on a primary, that will basically on a secondary will be 10 amps. So now this capacitor is low voltage, low current, and the output doesn't have that capacitor and so on. So you have everything what's needed, not only for a very demanding microprocessor drive, but isn't it great now for the point of load converter, right? When you want to say 48 volt down to 3 volts, 48 volt to, and maybe for that point of load, you never cared to get a large transient and fast transient, but why not if you get it for free, right? And it is smaller than anything else because two converters together make it really ripple free and so on. Oh, Jitendra, are you talking?
Yeah. Can you see me?
We see you all, and I'm going to give you the podium so we can all see you. Go ahead.
Yeah. So just wanted to understand from you the regulation loop of the converter which you just shown. Any feedback regulation is required for the converter which you have shown?
Okay, great question, because there's even better answer. You know what's the answer? No, I don't need and I don't want the feedback. And I don't know if you missed that. I mentioned it some of the earlier presentation in the last 2 weeks. When I go in a detailed presentation of this converter, you'll find out that this converter never goes to discontinuous inductor current mode. It is diode is always operating with a DC current level and sine wave current as opposed to sine wave current sine wave current superimposed to DC current is a twice the DC current magnitude. So it always start on off period, it always start at 0 and comes out of 0, which by definition, that means first and the only converter ever that never goes in discontinuous conduction mode, which I call discontinuous inductor mode versus, because in Ćuk converter, you have also discontinuous capacitor voltage mode. So basically, never changes voltage conversion ratio. That's a basic thing, because buck converter and all other converters that we know, conventional converters, because of buck converter, because of the boost converter, they all go at light load. They go to the mode which is not function of duty ratio. It is function of load current. And you're down at the 10% load current. And what happened? Now you must use feedback, because otherwise your voltage will go all the way up. So when you move into discontinuous conduction mode, then you have to use a feedback. But now the basic property of this converter, as I mentioned, is DC current superimposed on an AC ripple, and because it AC ripple is twice the peak to peak ripple is twice the DC current, or magnitude of this sine wave is equal to the output load, it automatically adjusts every cycle, okay? So it never goes discontinuous current. If that is the case, that's the number one requirement, that I can eliminate discontinuous conduction mode. What is the number two requirement? If it's 80%, I'm sorry, I still have to use the feedback, because 80% efficiency at the full load will mean if I go to 10% load, 5%, I get much less conductive losses of resistors or inductors and so on, transformer. These conductive losses will change dramatically. So now I cannot maintain output voltage constant if my efficiency is 80%. But guess what? And my efficiency will be 80% if I still have a problem with these three switches, two transistors on the input. They have, they're switching losses, and because there is, overlap of conduction, like in a Ćuk converter, square wave voltage, square current, but during that instance of transition, you have product of the two, and that's a big, at every transition, you have a big power loss, right? So that's one loss if it is have a regular converter, and the second loss is output diode. The output diode will have a square wave current and will have a switching losses as well. So you have all three switching losses. So how can you now not close the feedback loop if you have at the top of the switching losses, you have losses on these resistors and so on, magnetics losses, etc. So what is the other imperative? We got to have efficiency over 99%, hopefully 99.5%. Once you have that efficiency, then you can go 10% to 100% load, and you will have some effect of the resistances. But that effect is second or third order effect. And can I, someone asked me before, can I handle that without feedback? Why not? I have a working table and I sense the current, and with the same current, I have a table, and I said, if current is 100%, this correction is this much, for duty ratio current is 10%, correction this way. So I have an internal open loop feedback, like I told you, like a space shuttle. You're adjusting it with the open loop, right? So you basically don't have a feedback. You know, feedback was great in the good old days. We have a lousy converter, a lousy efficiency mode operation. That was all handled by an analog circuit and feedback. I don't need that. And why do I don't, not only I don't need it, I don't want it.